Good morning, everyone. How are you? I hope all of you are doing well and ready to dive into a new topic today or new thing. So, we are going to ask a question. Can light come out of silicon? Can we generate light from silicon? We have seen that when we, in one of the application where we were talking about different avatars also, and we saw that silicon, or in even generation recombination video, we talked about when we are shining light on silicon, right? We can generate what we call as the electron and hole pair, right? They are generated as result of light. And when we put in an electric field or some kind of junction where we can separate them out, right? We can separate them out, then there is a possibility that we can generate some current, right, using this light. That is what the one of the thing which we saw as a principle, guiding principle in the solar cells, right? Now we are going to talk about something opposite of that. We are talking about, okay, so let's say I have silicon, and when I apply an electric field, right, through a battery, apply an electric field through the battery, can I generate light? Can there is a possibility of light coming out of this, right? What is the physical principle of this thing? That is what we are going to talk about in this video. So what is basically decides that when does light come out? When I'm applying an electrical engineer, right? So electrical energy. So the idea is that we want to convert the electrical energy to the light, right? That is the basic idea. How we did in the solar cell when we converted the light or the photons to electrons, right? That is what which gave us the electrical current. So now, is this possible? And if it is not possible, why? That is what. And if it is possible, then where is it possible? Right? That is how we are going to ask these 3, 4 questions and try to answer what is happening there. So when we say light, what is light, first of all? And we, as it was talked about, so let's denote it a different. By Einstein, this is a packet of photons, right? There are photons which are there in light, which are another particle, like similar to electron or holes. Holes is though is an imaginary particle, but similar to electrons, phonons, and phonons also we have talked about. Let me just review what we talked about in one of the video. I think in generation recombination itself, we talked about phonons also, which is just the lattice vibrations. So that means the atoms moving, or atoms, a simpler way of saying that, moving or vibrating atoms, right? Vibration is important because moving means that it has gone away from the crystal. No, it is still very much part of the crystal, right? Whatever these atoms are, but they are vibrating in a sense that because there are electrons hitting them, or there are thermal energy in the system, right? Which so then this is what causes this vibration, which is what known as phonons, right? These lattice vibrations. So we have seen electrons, we have seen photons, which is in the light, we have seen phonons, right? So now based on this, we would be able to see what is that, which is when I want electrons to drive or give me photons. When do I do that, right? How do I do that? That is the question we are asking. So one of the way you can see that if there was a possibility that, let's say, this thing is at floor 0, right? This is at floor 1, which is our conduction band. This is floor 0, right? That has been our guiding principle. And let's say by some means you put this electron into the floor 1. Now the question is, when it comes back, and this is what again goes back to our idea which we have discussed. If you have not watched that video, do watch how the life birth happens of electrons and holes inside the semiconductor in a video called generation recombination, right, phenomena. So there we saw that there were two kind of way that this electron can come back. One is that it can, wherever it has left a hole, right, it comes back exactly there. And when we say this, we are not talking just in space, right? We are talking in terms of, now let me define something called, so this is, we know this is the energy axis for us, where there's energy. Now we know that because the electron is moving, right, in space, that means it has a velocity also, right? A particular velocity that it moves with. And this velocity we can define, also relate of the electron to something called the momentum of the electron, right? And I think this you know already, right? What is momentum? So momentum is very similar to a ball's momentum, but here we are putting this momentum as the, which is also known as wave number, right? And where this concept is coming from, the momentum, because we have said, okay, the electron which is there for us, it is moving. That is the picture you are telling me. There's mv associated with it. But we know that this is also, rather than just a particle, this is also a wave. And who told us this? That this is the duality which we talk about of the electron, that it can be a particle, it can be treated as a wave, right? And then in this duality, what comes out is very important relation, which is what we know as the, this thing which we were writing, right? So this guy is, yeah, is M also. So that means now I know that Planck is what related this thing. This wave number is similar to 1 by or 2 pi by lambda. And lambda we very well know from the waves is the wavelength, right? That means it's a wave, which relates to the wave number, right? And Planck constant is what puts this together, these two duality. Okay, it's the same thing we are talking about even in particle space, is the same thing we are talking about in the momentum space. So then what you see is that basically your mv, or this velocity, is can be expressed in terms of your momentum, right, or the wave number. This is largely, we say momentum because we know that, let's say if we were to describe this as a p, this momentum, right, which is the typical symbol we use, p is momentum. So why we say k is momentum, or loosely, is because we know p by h cross is your wave number we are talking about. So then h cross, because it's a constant term, so this can be also treated as the momentum of the particle, though we know that it has to be divided by h cross, right, to become a momentum. So then one knows, okay, that this is when we are talking about this particular momentum and of the electron. That means it does have energy and it also has a momentum, right? Now, when we talk about electrons, because it is inside a crystal, it would have both energy and momentum, right? So as of now, we are going to limit our discussion there itself, that electron has energy and it has momentum also. Momentum means because it's a moving wave or moving particle, right? So now the question which comes very appropriate is that what is the role of this momentum? Let's say, okay, I am going up, I am coming back. That means I am gaining energy, right? And I'm coming back. This is losing energy. So then why do you say that there are two different possibilities which you described in the video of generation recombination? You said there are two possibilities when it comes back, which are, you name it as non-radiative recombination, right? And then you say radiative recombination. Now you say, what does it mean, the radiative and non-radiative, right? Where does it come from? And then this is the very much the idea now we are going to discuss. See, in both you are losing energy, but what is happening in one is, in one, when you say non-radiative, your momentum, when the electron is coming, the momentum is also changing. Energy is going down, but momentum k is also changing, right? So that is the what is happening in non-radiative. Energy going down, k is changing, right? What happens in radiative, that your energy is going down, but k does not need to change, or it does not, should not change, right? That is what. And now the question you can ask is, where does this come from? Where does it, why you say that k is very important? That in this we discussed, again backing to my video of the generation recombination. Here we said that only thing which comes out is heat, which is your lattice vibrations or phonons. Here, this is the important part we are talking about, where the light comes out, which is your photons, right? So that is the basic principle in bringing or getting the light out of the semiconductor through this recombination process, right? Now the question which is that when you say that k does not need to change, why is it that when k is changing, light is not coming out, right? That is the question you are asking. So when k changes, why photon can't come out, right? Why is it not giving enough as a photon? And that is the question which you can explore in the, that okay, my energy of the photon, if it is h nu, right, which is the frequency or of the light, and we know that okay, what is the speed of light and all those things, then you know from that, which is sc by lambda, right? If you were to now calculate the phonon, because we were to relate in the same way this momentum of the photon, if we were to get the momentum, right, we can calculate k from here. You will see it comes to be very, very small momentum, right? So this momentum which comes out from this is an energy. You see, this comes out to be very, very small. That means it's very likely, what we can say is, the photon can have energy, right? Because obviously, because it has energy, that's why it is hitting and giving that energy to the electron. But it cannot, it can, it does not, it does not carry momentum, right? Because momentum is very, very small, so it does carry energy, right? So now from that perspective, one can see, oh yeah, the momentum, why it does not change, or why it does not need to change when the photon is, or we want photon to come out, is because the photon itself is not carrying that property, while phonons is a very good way to, when you are changing the momentum, or you have the momentum to change, phonons will help you, right? So these are the two people who says, okay, if you have an electron which is coming from here, so let me draw in the space now of E and K. So let's say this is energy and this is my K, right? Let's say there is a floor 1 here, which is floor 1, and the floor 0 is here, right? Because that is what the meaning of the 2 energy will be. So this is my, it's a 1 energy, this is my Emax and Emin, right? This is your floor 0. But they are not, the two floors are not made on top of each other. In the sense, in the momentum space, what you see, that they are not on top of each other, which is why the electron, so let's say there is an electron which is here, right? Yeah, an electron, it wants to come back to floor 0. It sees that I have to change my momentum if I want to go back to my floor 0, because it is somewhere shifted in the momentum domain. That means I have to change my momentum if I want to go back to floor 0, right? That is what it would mean. So now that means that this k needs to change, right? And that is the very much reason, and this is what we know as typically in the semiconductor world, we know as an indirect semiconductor, indirect bandgap semiconductor, right? Meaning that you have to change, you have, when you have these two bands or two floors, they are at different k, right? That is what the meaning is. So when you change this to this, you will change the k, right? That is the basic idea. What is going to happen, the k needs to change, right? And that is the reason that the photon, whenever this happens, photon cannot come out, can't come out, because photon cannot carry that momentum. Then who has to carry that momentum? Phonons. Phonons, if they carry, they come out at heat, right? Only heat is generated, right? Photons are not, if it is coming down, right? So that is why you need some other kind of semiconductor. So this is the case which you rightly guessed is your silicon, where it's the indirect band gap. Why? There are different kind of semiconductor where I have floor 1 and I have floor 0, they are on top of each other, right? That means in the K space, if I look at, they are on top of each other. That means when this electron wants to come back, it finds the same K. It can find the same K. It does not need to change the K. And that's why the photon can come out of this. And these semiconductors are called direct bandgap semiconductor. And an example of this is your gallium arsenide, right? So these are gallium arsenide or 3,5 materials like indium phosphide. So these are the materials or different kind of materials where this momentum plays a very important role. So that means the light cannot come out of silicon. That is the answer, right? Because it has an indirect band gap, because it has to change the momentum when the electron comes back to the floor 0. It has to change the momentum because this is the energy which is going out somewhere, right? So this cannot come out in light, the photon, because the momentum is changing. Here the momentum is not changing, that's why there is a possibility of light or photon coming out, right? So that is what is the basic idea of what I tried to explain today, in that what is the indirect and direct band gap application. If we just study that, you may not be able to appreciate, but probably today you will be able to appreciate, because there is an application of this very much the direct band gap, or how the electron comes back to the valence band defines that the light is coming out of or not. And that is what is used in lasers, the same concept, lasers, right, where we are generating this light coming out of this. Okay, so that is all, and thank you, and keep learning all of you, and see you in the next video. Bye bye.